You will need to know calculus in this course, so in this lesson, we will review derivatives. This expression, y equals y parentheses x, means y is a function of x. When we read it, we say y equals y of x, or we say y is a function of x. The derivative of y with respect to x is typically represented by the symbol y prime or dy over dx, or we can also write it as y prime of x instead of just y prime, to explicitly say that the derivative is with respect to x and that the derivative is also a function of x. Given how y depends on x, how do we determine the derivative of y with respect to x? Here's what we do. First, we derive the expression for the ratio of delta y to delta x. In general, this ratio will depend on x and delta x. Then, we take the limit as delta x approaches 0. When we do, we get an expression that no longer depends on delta x, but generally still depends on x. What do delta x and delta y mean in the expression we have here? Delta x means a change in the value of x. If x changes by an amount equal to delta x, then the corresponding change in the value of y is delta y. What do we mean by the limit as delta x approaches 0? It means what the expression becomes as delta x becomes very, very small. We can think of the dx in dy over dx as a very small delta x. It is often described as an infinitesimally small change in x. Let's take a look at an example. What if y is equal to mx plus b, where m and b are constants? What function would we get if we differentiate y with respect to x? The word differentiate means take the derivative of. Recall that the derivative of y with respect to x is defined as the limit as delta x approaches 0 of delta y over delta x. Let's first derive the expression for delta y. We are given that y equals mx plus b. In other words, whatever x is, we multiply it by the constant m, then add the constant b. What happens if x changes by an amount equal to delta x? We substitute x plus delta x for x, multiply it by m, then add b to get the new value of y. From this, we subtract the original value of y, which is mx plus b. In order to get delta y, we can simplify the expression for delta y. And we should get delta y equals m times delta x. Dividing both sides of this equal by delta x, we get the ratio of delta y to delta x, which we can simplify to just m. So what happens when delta x becomes very small? This ratio is still equal to m since m is a constant. Therefore, if y is equal to mx plus b, the derivative of y with respect to x is equal to m. We can also say that the derivative of mx plus b with respect to x is equal to m. We can also say that y prime of x is equal to m. Recall that the equation y equals mx plus b is the equation of a straight line with a slope equal to m and y-intercept equal to b. In other words, the derivative of a linear function of x is just the slope of the line. It is a constant. It doesn't actually depend on x. However, in general, the derivative will depend on x. Given that y is equal to 3x plus 2, what is the derivative of y with respect to x? We can see that the equation we have here is of the form y equals mx plus b. It's an equation of a straight line. A plot of y versus x is a straight line with a slope equal to m. We have seen that the derivative of this function is just the slope of the line. In this case, the slope is equal to 3. Therefore, the derivative of y with respect to x is equal to 3. How about the function y equals 5? What is the derivative of y with respect to x? This is the same thing as y equals 0 times x plus 5. This is the equation for a horizontal line, a line with a 0 slope. Therefore, the derivative with respect to x is 0. Think of it this way. Since y is a constant, it doesn't really depend on x. Regardless of delta x, we expect no change in y. Delta y is 0, so delta y over delta x is 0. In other words, the derivative of a constant is 0. What if y is equal to x squared? What function would we get if we differentiate y with respect to x? Recall that the derivative of I with respect to x is defined as the limit, as delta x approaches 0, of delta y over delta x. Let's first derive the expression for delta y. We are given that y is equal to x squared. In other words, whatever x is, we square it to get y. What happens if x changes by an amount equal to delta x? We substitute x plus delta x for x to get the new value of y, which is the square of x plus delta x. From this, we subtract the original value of y, which is x squared, in order to get delta y. The square of x plus delta x is x squared plus 2 times x times delta x, plus delta x squared. Subtracting x squared, our expression for delta y simplifies to delta y equals 2 times x times delta x plus delta x squared. Dividing this expression by delta x, we get delta y over delta x equals 2 times x times delta x plus delta x squared divided by delta x, which can be simplified to 2 times x plus delta x. So what happens when delta x becomes very, very small? This expression becomes 2 times x plus a very small number. This expression reduces to just 2x. Therefore, if y is equal to x squared, the derivative of y with respect to x is equal to 2x. We can also say that the derivative of x squared with respect to x is equal to 2x. We can also say that y prime of x is equal to 2x. Note that differentiation, or take the derivative of a function with respect to x, just gives us another function of x. Here's a list of functions for which you should know the derivatives by heart. Although those can all be derived from the definition of a derivative, it is best to just memorize them. You will be needing these a lot, so you should be able to recall these as quickly as recalling that 1 plus 1 equals 2. If y is equal to a constant, the derivative is equal to 0. If y is equal to x raised to the power of n, then to get the derivative of y with respect to x, lower the exponent by 1, then multiply by n. Please note that n here does not have to be a positive integer. It can be any real number. It can be a fraction, and it could be negative. If y is equal to sine of x, the derivative is equal to the cosine of x. If y is equal to the cosine of x, the derivative is equal to the sine of x. For the function e raised to the power x, the derivative is also e raised to the power x. You may also see e is to the power x written as exp followed by x in parentheses. We read it as exp of x. Finally, if y is the natural logarithm of x, the derivative is 1 over x. The natural logarithm of x is often written as ln of x, or as log of x to the base e. Just in case you haven't seen e before, it's called Euler's number. It's the limit of the expression 1 plus 1 over n raised to the power n as n approaches infinity. Euler's number is an irrational number that is with a non-terminating, non-repeating decimal. To 3 significant digits, it's 2.718. The volume of a cube with the side of length L is equal to L cubed, or L raised to the power 3. What is the derivative of v with respect to L? Recall that if y is equal to x raised to the power n, then the derivative of y with respect to x is n times x raised to the power n minus 1. So if y is x to the power 3, then n is 3, and the derivative is 3 times x raised to the power 3 minus 1. Since 3 minus 1 is 2, the derivative is 3x squared. In the expression v equals L cubed, we can think of v as y, L as x, and n as 3. In other words, we could say that y is equal to x cubed, just as v is equal to L cubed. So the derivative of v with respect to L is 3L squared. You need to get used to using other symbols besides x and y. When dealing with physical quantities, it is preferable to use symbols that closely resemble the names of the quantities. Here's a list of identities involving derivatives that you should know by heart. All of these can be derived from the definition of a derivative, but it's best to memorize them. If you know these and the derivatives of the 6 simple functions introduced earlier, then you will be able to easily differentiate most of the functions that you will encounter. If f is a function of x and you multiply it by a constant c, then the derivative of the resulting function can be obtained by taking the derivative of f, then multiplying the result by c. If f and g are both functions of x, then the derivative of their sum or difference is equal to the sum or difference of their derivatives. Take the derivative of f alone, take the derivative of g alone, then add or subtract as the case may be. What about the product of two functions of x? To get the derivative of the product, we multiply the first factor by the derivative of the second, then we multiply the second factor by the derivative of the first, then add the two products. This formula is known as the product rule. Finally, let's talk about the chain rule. This is a very useful identity. It says if f is a function of g and g is a function of x, then the derivative of f with respect to x is equal to the derivative of f with respect to g times the derivative of g with respect to x. It's easier to remember the chain rule by writing the derivatives this way. We can see that df is in the numerator on both sides of the equation, and dx is in the denominator on both sides of the equation. And we can think of dg as canceling out. At this point, you may be wondering why I did not introduce the identity for our division, which you probably encountered in calculus class. The reason is that division is equivalent to multiplication by the reciprocal. This means that if you need the derivative of f over g, you just need to take the derivative of f times reciprocal of g. So you can apply the chain rule and the product rule. It's just one less identity that you need to memorize. Let's take a look at a few examples. Here are some examples. Suppose y is equal to 3x squared. The derivative of y with respect to x is the derivative of 3x squared with respect to x. Here we have a constant, 3, times a function of x, which is x squared. We can factor it out to 3. So the derivative is equal to 3 times the derivative of x squared. The derivative of x squared with respect to x is 2x. 3 times 2x is 6x. What if y is equal to x squared plus x cubed? We can see that here we are looking for the derivative of a sum of two functions, x squared and x cubed. So we can take the derivatives of the functions separately first, then add the results. This gives us 2x plus 3x squared. The derivative of x squared is 2x, and the derivative of x cubed is 3x squared. Here's a simple example illustrating the rule for taking the derivative of a product of two functions. Suppose y is equal to x squared times x cubed. Then the derivative of the product is equal to the first function, which is x squared multiplied by the derivative of the second function, plus the second function, which is x cubed multiplied by the derivative of the first function. Please note that it doesn't matter which function you want to call the first function and which one you want to call the second function. Let's go ahead and simplify our expression for the derivative. The derivative of x cubed is 3x squared. Multiplying it by x squared gives us 3x to the fourth power. The derivative of x squared is 2x. Multiplying it by x cubed gives us a 2x to the fourth power. Adding 3x to the fourth power and 2x to the fourth power gives us 5x to the fourth power. Here's another way we could have obtained the derivative. We know that x squared times x to the third is equal to x to the fifth. If we take the derivative of x to the fifth, we get the same answer, 5x to the fourth. It might seem like using the product rule unnecessarily made it more cumbersome to get the derivative. That's just for the specific, very simple example. In general, it would be much more convenient. Here's a simple example illustrating the chain rule. Suppose y is equal to u squared and u is equal to x cubed. According to the chain rule, the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. Since y is equal to u squared, the derivative of y with respect to u is equal to the derivative of u squared with respect to u, which is equal to 2u. Since u is equal to x cubed, the derivative of u with respect to x is equal to the derivative of x cubed with respect to x, which is equal to 3x squared. So, the derivative of y with respect to x is 2u times 3x squared, or 6u times x squared. However, we want to express our derivative as a function of x, so we replace this u by x cubed since u is equal to x cubed. 6 times x cubed times x squared gives us 6x2. Here's an alternative way of determining the derivative. Starting with y equals to u squared, we replace u by x cubed. We can see that x cubed square is x to the power 6. So the derivative of y with respect to x is the derivative of x to the power 6, which gives us the same answer, 6x to the 5th. It may seem like using the chain rule is more cumbersome, but that's only in this specific very simple case. In general, you will find that the chain rule is quite convenient. The compressibility factor, Z, of a real gas at sufficiently low pressures is a function of the molar volume V sub m. The relationship is given by this equation, C is equal to 1 plus B over V sub m. What is the derivative of Z with respect to V sub m? In this equation, B is a constant. The function does not look like any of the simple functions for which we know the derivative. So let's try to break it up using the identities. First of all, we can see that z is a sum. The derivative of sum is equal to the sum of the derivatives. So we can write the derivative of z as the derivative of 1 plus the derivative of b over v sub m. The derivative of a constant is 0, so the derivative of 1 is 0. Here, our x is v sub m, which is in the denominator. None of the simple functions for which we know the derivative has x in the denominator. It's okay. We just need to move the entire expression in the denominator to the numerator, but raise it to the negative 1 power. So we can rewrite b over v sub m as b times v sub m raised to the negative 1. Since b is a constant, what we have here is a constant times a function of v sub m. So we can pull the b out and we get b times the derivative of v sub m to the negative 1. The derivative is like the derivative of x to the power n, except that in this case, x is v sub m and n is negative 1. So the derivative of v sub m to the negative 1 is equal to n, which is negative 1, times v sub m raised to the n minus 1. Note that n minus 1 is negative 1 minus 1, or negative 2. The expression simplifies to negative b times v sub m raised to the negative 2. Finally, since v sub m raised to the negative 2 is 1 over v sub m squared, we can also write the derivative as negative b over v sub m squared. The dependence of the ground state wave function psi of a harmonic oscillator on its location is given by the equation psi equals n times e to the negative alpha x squared. What is the derivative of psi with respect to x? In this equation, n and alpha are constants. Overall, the function does not look like any of the simple functions for which we know the derivative. So let's try to break it up using the identities. First of all, we can see that psi is a constant times a function of x. So we can factor out the constant n, and we can get n times the derivative of e to the negative alpha x squared with respect to x. We know the derivative of e to x with respect to x is e to the x. But here we have e to the negative alpha x squared. We can make things easier if we use the chain rule. So let's define function u as negative alpha x squared. So e to the negative alpha x squared becomes e to the power u. Now we can use the chain rule. This is the derivative of e to the u with respect to x. The chain rule says it's equal to the derivative of e to the u with respect to u times the derivative of u with respect to x. So now we have derivative of psi with respect to x equals n times the derivative of e to the u with respect to u, which is just e to the u, times the derivative of u with respect to x, which is equal to negative alpha times 2x. One last step we need to do is to get rid of u in the final expression. Remember that u is negative alpha x squared. Therefore, e to the u is e to the negative alpha x squared. So the derivative of psi with respect to x is n times e to the negative alpha x squared times negative alpha times 2x. The first excited wave function psi of a harmonic oscillator depends on its location x according to the equation psi equals n times x times e to the negative alpha x squared. What is the derivative of psi with respect to x? In this equation, n and alpha are constants. The function does not look like any of the simple functions for which we know the derivative, so let's try to break it up using the identities. We can see that psi is a constant times a function of x, so we can factor out the constant n and we get n times the derivative of x times e to negative alpha x squared with respect to x. Here we have a product of two functions, x and e to the negative alpha x squared. So we can use the product rule. The derivative of the product is equal to the first factor, x times the derivative of the second factor, plus the second factor, e to the negative alpha x squared, times the derivative of the first factor. The derivative of x with respect to x is obviously just equal to 1. And earlier, we found the derivative of e to the negative alpha x squared to be e to the negative alpha x squared times negative alpha times 2x. The only thing we have left to do is make the substitution to get the expression for the derivative of psi with respect to x as a function of x. The second derivative is defined as the derivative of the derivative. In other words, you perform two consecutive differentiations to get the second derivative. Here are the most common ways of representing the second derivative of y with respect to x. We read this as y double prime. We put two prime symbols next to y. We can also write it this way. Instead of dy over dx, we write d squared y over dx squared. Note that the superscript 2 is written next to the d in the numerator and next to the variable in the denominator. Here, the variable in the denominator is x. This one is a straightforward way of saying that we are taking the derivative of the derivative. When we take the derivative of a function, we can also write the function next to d over dx. So this expression means derivative with respect to x of the derivative with respect to x. Let's take a look at a simple example. What is the second derivative of x cubed? The derivative of x cubed is 3x squared. This is also called the first derivative. The second derivative is the derivative of the first derivative. By now, you should be able to easily figure this out to be 6x. We saw that if a function describes a straight line, the derivative is equal to the slope of the line. In other words, if y equals mx plus b, where m and b are constants, then the derivative of y with respect to x is equal to the slope m. We can extend the concept of slope to functions that do not describe a straight line. We can define the derivative as the slope of the curve. Let's look at a specific example. Here's a plot of y versus x if y is equal to x squared. Notice that the plot is not a straight line. Previously, we have shown that the derivative of x squared is 2x. Let's examine the point at x equals 1. Y is 1 squared, so y is equal to 1. Here's the point. Remember that the derivative at this point is 2x. Since x is 1, the derivative is 2 times 1, or 2. We say that the slope of the curve at this point is 2. To visualize what this means, imagine a straight line with a slope of 2 that goes through this point. Here's this line. To convince yourself that the slope is 2, examine this line carefully. You can see that the line rises by 2 units, from -1 to +1, when x changes by 1 unit from 0 to 1. We refer to this line as the tangent line, or the line that is tangent to the curve at x equals 1. For comparison, let's examine that point at x equals 2. 2 squared is 4, so y is equal to 4 when x is 2. Here's the point. The slope at this point is equal to the derivative, which is 2 times x or 4. Here's the tangent line that goes through this point with a slope of 4. We can see that the derivative at x equals 2 is bigger than the derivative at x equals 1. We can see that from the graph that thinking of the derivative as a slope is consistent with our qualitative notion of steepness. An important application of derivatives is an optimization. When we try to optimize something, we want it to either have a maximum or minimum value. Consider the function shown in the animation below. The animation shows what happens to the tangent line as a function of x. Remember that a steeper uphill slope means a more positive derivative. A steeper downhill slope means a more negative derivative. And a horizontal line means a zero slope. We can see that the function peaks here. We call this location a local maximum. We say local because we don't know if the function has a much higher peak somewhere else. To the left of this location, we can see that the slope of the tangent line is positive, but the slope decreasing. It's getting less and less steep as you approach the peak. The tangent line becomes flat when you're at the peak, so the derivative at the peak is 0. Past the peak, we can see that the slope of the tangent line becomes negative, so the derivative is still decreasing. Since the derivative is decreasing as you go through the peak, we can say that the second derivative is negative in the vicinity of the peak. In a region where the second derivative is negative, we can describe the shape of the graph as concave down. The important lesson to learn here is if we want to solve for the location where a function is at a maximum, we take its derivative, then solve for the x value that would make the derivative equal to 0. However, just because the derivative is 0 at a given location does not necessarily mean that the function has a maximum there. It could also be a minimum. Here's a location where the function is at a local minimum. We can see that the tangent line has a negative slope just before this location. But the slope becomes less steep, which means it becomes less negative, so it's increasing. We see that the tangent line becomes horizontal at the local minimum. So, the derivative at the local minimum is 0. Just past the local minimum, the slope of the tangent line becomes positive. So, the derivative increases as we go through a local minimum. So, in the vicinity of the local minimum, we can say that the second derivative is positive. The shape of the graph associated with a positive second derivative is said to be concave up. So far, we've seen that a 0 derivative is associated with a local minimum or maximum. If we want to know if the location is a minimum or maximum, we examine the trend in the first derivative just before and just after the location. Or we can use the second derivative test. At a local minimum, the second derivative is positive. Earlier, we saw that the second derivative is negative at a local maximum. But what if the second derivative is 0? A location where both first and second derivatives are 0 can be a local minimum, local maximum. Or it can be neither. The third possibility is called an inflection point. An inflection point is a location where the plot of a function switches from concave up to concave down, or from concave down to concave up. Since the second derivative is positive in regions where the plot is concave up and negative in regions where it is concave down, the second derivative must be 0 at the inflection point. However, the converse is not necessarily true. If the second derivative is 0 at a location, it may not be an inflection point. Earlier, we said that if both first and second derivatives are 0 at a given point, then it could be local minimum, a local maximum, or an inflection point. One way to know, as we've seen earlier, is to examine the derivatives before and after the location. The derivative goes from negative to positive across a minimum. The derivative goes from positive to negative across a maximum. Here's an example of a function with an inflection point. Here, y is equal to x cubed. The plot is concave down at x less than 0 and concave up at x greater than 0. So x equals 0 is an inflection point. At x equals 0, both first and second derivatives are 0. The slope becomes less steep and approaches 0 as x approaches 0. But the first derivative is positive on both sides. A derivative describes how a very small change in one variable affects another. For example, if y is a function of x, then the derivative of y with respect to x, which is written as dy over dx, is the ratio of the changes in y and x if the change in x is very, very small. A very small change in x is represented by dx, and the corresponding change in y is represented by dy. For a given x value, this ratio is unique. In general, quantities can depend on more than one independent variable. For example, what if y is a function of w and x where w and x are independent variables? How do very small changes in x affect y? Well, for a given x, the ratio of the changes is no longer unique. It will depend on what w is. So we give the ratio a different name. We call it a partial derivative of y with respect to x, and instead of using the letter d, we use this symbol instead. This is called the partial symbol. And the partial derivative of y with respect to x is written like this. Note that the partial symbol looks like the lowercase Greek letter delta, but it's not the same. So don't use lowercase delta when writing partial derivatives. The rules for taking partial derivatives are the same as the rules for regular derivatives. We just need to treat all the other independent variables as constants. Here's an example. Suppose rho is equal to m over v. What would be the partial derivative of rho with respect to m? Let's work this out step by step. We substitute m over v for rho. We can write m over v as 1 over v times m. Since we are partial differentiating with respect to m, we treat v as a constant. So here we have a constant 1 over v times a function of m. We can factor out the constant. This gives us 1 over v times partial derivative of m with respect to m. Partial m over partial m is just 1, so our expression simplifies to just 1 over v. What about the partial derivative of rho with respect to v? This time we factor out m as a constant. This gives us m times the derivative of 1 over v with respect to v. Here, 1 over v is written as v to the negative 1 power. The derivative of v to the negative 1 is negative 1 times v to the negative 1 minus 1. After simplification, we get negative m over v squared as the partial derivative of rho with respect to v.